Welcome to For the Love of Physics podcast. We are Mr. Jager's assistant.
Hello, everyone.
And today we're diving deep into a really fundamental concept. I know many of you at Ishik Boys High School are probably looking at this right now in Mr. Jager's class.
That's right. We're talking about the conservation of momentum.
Exactly. And our mission really is to take this core idea, the kind you find in a textbook, and just bring it to life a bit.
Make it connect with the real world. Link it back to what you're actually learning.
Yeah, we're basically pulling from your high school physics textbook, looking at how stuff interact.
Trying to get those key insights for you.
Okay, so let's start with maybe a concrete example. Something easy to picture.
Good idea.
Imagine like a really smooth gym floor, almost no friction.
Like an ice rink, practically.
Yeah, and you've got two soccer balls. Ball A is rolling along.
Okay.
And ball B is just sitting there, totally still.
Right.
What happens when A hits B?
Well, obviously ball B is going to start moving. And ball A, it'll probably slow down, maybe even stop, depending on the hit.
Okay, but the physics part, the momentum part, that's where it gets interesting, right?
That's the key. Before the collision, ball A has momentum. It's got mass and velocity.
And ball B.
Zero momentum. It's stationary.
So during the hit, things change. Tell us about that shift.
Okay, so ball B gains momentum, obviously, because it starts moving. And ball A, it loses some.
Right.
But here's the really cool part, the elegant bit. The amount of momentum ball A loses is exactly the same amount that ball B gains.
Exactly. Like perfectly balanced.
Perfectly balanced. It's like a neat little transaction. Your textbook, Table 6.1, probably shows numbers for this.
It does, yeah. Ball A starts with 0.480 kilogram meters per second.
Right. And ball B starts with 0, so the total initial momentum is just 0.40.
And after they collide, the table shows ball A slowed way down, only 0.02 units of momentum.
Okay, but ball B picked up 0.38.
So 0.02 plus 0.38, that's 0.40 again?
Right, exactly. The total momentum after the collision is still 0.40 kilogram meters per second. It stays the same overall.
Wow. That's neat. And that's not just for soccer balls, right? This is a bigger thing.
Oh, absolutely. This is the law of conservation of momentum.
Okay.
The formal way to say it is something like, the total momentum of all objects interacting with one another remains constant regardless of the nature of the forces between the objects.
That sounds official.
It is. And there's an equation for it too, which is super useful. For two objects interacting, like our soccer balls, it's m1v1 I plus m2v2 I equals m1v1 F plus m2v2 F.
Okay, let me break that down. M1v1I is mass 1 times its initial velocity, plus M2v2I, mass 2 times its initial velocity.
Right, the total momentum before they interact.
Equals M1v1 F, mass 1 times its final velocity, plus M2v2F, mass 2 times its final velocity.
The total momentum after they interact. It just means total initial equals total final. Simple, but powerful.
That equation makes it really clear. Now, you mentioned interacting objects. Is this idea of an isolated system important here?
Crucial. Yeah. An isolated system basically means we're only considering the objects doing the interacting, like the two soccer balls.
And nothing else is interfering.
Right. Like our smooth gym floor example assumes no friction, no air resistance, nobody kicks the ball during the collision. If there are other forces, like friction or maybe gravity playing a big role, then to still use the law, you have to include those things in your system.
Okay, so the system might need to get bigger depending on what's happening.
Exactly. You have to account for all the significant interactions.
Got it. So it's not just collisions then. Does this conservation thing work if things push apart, like starting from rest?
Oh, definitely. Think about two ice skaters standing still, facing each other on the ice.
Okay, total momentum is 0, right? Nothing's moving.
0. Now, they push off each other. What happens?
They both move backwards, away from each other.
Right, in opposite directions. Skater 1 gains momentum one way, skater 2 gains momentum the other way.
But wait, if they have equal mass and push equally?
Their momentums will be equal in magnitude, but opposite in direction. So if you add them together, one positive, one negative.
They cancel out. The total is still 0?
Still 0.
Yeah.
The total momentum is conserved, even though they started from rest and pushed apart.
Okay, that makes sense. But now for something mind-bending. What about me jumping?
Yes. Go on.
When I jump up, I start at rest, 0 momentum. Then I'm moving upwards, so I definitely have momentum, right? Mass times velocity.
You do. So your momentum isn't conserved, clearly.
Oh, yeah.
It changed from 0 to something.
Right. So how does the law apply here?
Well, remember, the isolated system.
Yeah.
You jumping isn't just you. You pushed off something.
The Earth.
The Earth. If you include the Earth in your system, then the total momentum is conserved. When you push off the Earth to jump up, you exert a downward force on it. By Newton's third law, the Earth exerts an equal upward force on you.
Okay.
So if you gain, say, 60 kilogram meters per second of momentum upwards,
Yeah.
the Earth must gain 60 kilogram meters per second of momentum downwards.
Whoa. Wait. The Earth moves when I jump. Seriously?
Yep, equal and opposite momentum.
But why don't we feel the Earth shudder every time someone jumps? That seems impossible.
It comes down to mass. The Earth's mass is, well, it's enormous. About 6 times 10 to the power of 23 kilograms. It's huge.
Okay. Ridiculously big.
So even if it gains that 60 units of momentum, its velocity, VPM, is going to be incredibly, unbelievably tiny. Like 1 times 10 to the power of minus 23 meters per second.
So small, it's completely unnoticeable.
Completely. But technically, conserved momentum means it does move that tiny bit.
That's actually amazing. Okay, so if it works for jumping off Earth, what about space travel? Rockets in space. The Typemake has this great question. How does a spacecraft speed up or slow down in empty space? There's nothing out there for the rocket exhaust to push against, right?
Right, it's not like a car pushing against the road or a boat pushing against water.
So how does it work?
It's pure conservation of momentum again. The rocket engine throws mass hot gas out the back at very high speed.
Okay, so the gas has mass and velocity. It has momentum backward.
Exactly. A significant amount of momentum directed backwards.
Ah, so to conserve the total momentum of the system, which is the rocket plus the gas.
The rocket itself must gain an equal amount of momentum in the forward direction.
So it pushes itself forward by throwing its own mass backward.
Precisely. It doesn't need anything external to push on. The system is the rocket and its fuel. As it expels fuel mass, gas, the rocket gains momentum. It's a beautiful application of the law.
It really is. So all these examples, soccer balls, skaters, jumping, rockets, they all boil down to this conservation law. But what's the deeper physics? Why is momentum conserved? You mentioned Newton's third law earlier.
You got it. Newton's third law is the key. Let's think about bumper cars.
Yeah.
Fun, right?
And crash into your friends.
So 2 bumper cars collide. Let's call them car 1, M1, and car 2, M2. Yeah. When they hit, car 2 pushes on car 1 with a certain force that's called F1. And at the exact same time, car 1 pushes back on car 2 with a force F2. Newton's third law tells us these forces are equal in strength, but opposite in direction. So F1 equals F2.
Action-reaction pair. Got it.
Now remember the impulse-momentum theorem. It says that force multiplied by the time it acts gives you the change in momentum. Feet.
Right. Impulse equals change in momentum.
And here's the crucial bit. The time interval during which these 2 forces act is exactly the same for both cars. The collision lasts the same amount of time for car 1 as it does for car 2.
Okay, that makes sense. They're hitting each other simultaneously.
So if the forces are equal and opposite, F1 equals F2, and the time interval is the same,
Then the impulse on car 1, F1, must be equal and opposite to the impulse on car 2, now F2.
exactly, which means the change in momentum for car 1 is equal and opposite to the change in momentum for car 2.
So if car 1's momentum increases by, say, 100 units,
Then car 2's momentum must decrease by 100 units, or vice versa. The total change is 0.
and if the total change is 0, that means the total momentum before equals the total momentum after.
Bingo. That takes us right back to our conservation equation. M1v1, I plus M2v2, I equal M1v1, F plus M2v2F. It all stems from Newton's third law.
That's a really clear connection. Wow. Okay, one little detail though. You mentioned impulse F times delta T, but in a real crash, like with bumper cars or actual cars, the force isn't constant, is it? It spikes up and then drops down.
That's a very good point. No, it's usually not constant. It ramps up as the materials compress and then falls off. But for calculations, especially in introductory physics, we often talk about the average force over that time interval.
Oh, okay.
Using the average force gives the same total impulse, the same overall change in momentum, even if the instantaneous force varies. So it simplifies the math while still capturing the essential physics of the momentum change.
Gotcha. That makes sense for calculations. Okay, let's shift gears a bit. How does this understanding of momentum, impulse, and forces apply to something really practical, like surviving car crashes?
Oh, this is where the physics becomes incredibly important for safety engineering. It literally saves lives.
Yeah, the textbook mentions something really stark, like 2 cars hitting head-on at 100 kilometers per hour.
Yeah,
The energy involved is like falling off a 12-story building.
that's right. It's a huge amount of kinetic energy to dissipate, and it needs to happen very, very quickly in a crash. That rapid change in speed means massive acceleration and therefore massive forces.
So how do cars protect us from those massive forces? It seems impossible.
Well, engineers use the impulse momentum principle. Think about PhET. The change in momentum in a crash is fixed. You're going from your initial speed to zero.
Right, you have to stop.
So if PIP is fixed, how can you reduce the force, F?
You have to increase the time.
Exactly. You have to make the stop take longer. And that's what crumple zones do.
It's the front and back parts of the car that are designed to crush.
Precisely. They're made of pliable metal and structures that deform and collapse during impact. This isn't just damage, it's engineered.
How does the crumpling help?
It does two things. It absorbs some of the collision energy, turning it into heat, and the work of deforming the metal. But crucially, it increases the time it takes for the main passenger compartment and you to come to a complete stop.
Longer time, less force.
Much less force on the occupants. It makes a huge difference.
Okay, and what about seatbelts? We all know we should wear them, but how do they fit into this physics?
Seatbelts are another key part of extending that stopping time for your body. They aren't just rigid straps.
They stretch.
Yes, they're designed to stretch slightly during a severe impact. That little bit of stretch increases the duration over which your body decelerates.
Crane principle. Longer time, less force on my body.
Exactly. Dramatically less force. Plus, of course, they keep you from flying forward and hitting the dashboard, steering wheel, or windshield.
Which would obviously be bad.
Very traumatic results, as the textbook likely puts it. The forces involved in hitting a hard surface inside the car are immense.
This really highlights something else important. Why holding a baby on your lap in a car is so incredibly dangerous. It feels like you're protecting them, but...
Physics says absolutely not. It's about inertia and force. Even a small infant, say 20 pounds, which is about 89 newtons of weight.
Okay.
In a collision, the forces acting on that baby to decelerate them from car speed to zero could easily reach, the book suggests maybe 1780 newtons.
Wait, 1780 newtons, that's like 400 pounds of force.
Exactly. Can you hold on to 400 pounds suddenly appearing in your arms?
No way. Absolutely not. Your grip would break instantly.
Instantly. And because of inertia, the baby continues moving forward at the car's original speed until they hit something solid like the dashboard.
Oh, that's horrifying.
It is. It underlines why properly installed car seats are non-negotiable. They're designed to manage those forces and protect the child in ways our arms simply cannot.
Wow. Okay, so let's just quickly recap the big ideas from today's dive.
Sounds good.
We started with momentum itself, basically. Mass in motion, PMV.
Right. How much oomph something had.
Then the main event, the law of conservation of momentum. The total momentum of an isolated system stays constant.
Total before equals total after. We saw it in collisions like the soccer balls.
And in things pushing apart, like the skaters, or even me jumping off the Earth.
And in rockets in space.
We also saw how it connects directly back to Newton's third law: equal and opposite forces during interactions lead to equal and opposite changes in momentum.
Which means the total stays the same.
And finally, we saw how understanding impulse is critical for safety, how crumple zones and seatbelts work by extending the time of impact to reduce the force.
Making collisions survivable. It's physics in action, really.
Absolutely. It's amazing how one core principle explains so much.
Definitely. So maybe a final thought for everyone listening. A little something to ponder.
Yeah, let's do that.
Okay, here's one. If a superhero, like Superman, or someone incredibly strong, jumped off a planet,
Yeah.
really pushed off hard, would the planet's orbit change? Even a tiny, tiny bit? And why or why not, based on what we talked about today?
That's a good one to think about. Use that conservation of momentum idea. Okay, that's our deep dive for today.
Hope it's helpful.
Stay in contact with your physics teacher. Stay creative.